So it's a fairly, I guess, esoteric topic. You'll have to bear with me on this one. I do sort of reference thinking fast and thinking slow. If you haven't read the book, I highly recommend that you do. But it sort of frames the way that our brain works into two characters, System 1 and System 2. System 1 being the part of the brain that can answer questions quickly, and it does this based on intuition and things like that. Then you have the lazier side of your brain, System 2. It's the part of the brain that solves analytical problems. The thing is, it is lazy, and it likes to feed information, be it right or wrong, to System 1 so it can quickly answer questions. You'll also have to bear with me because I am attempting to do something new. I'm more used to talks where I deep dive into a particular topic. I'm going to try and cover a broad set of topics that aren't really JavaScript related. They're more theoretical, but definitely do have applications into everything we do day to day. I'm going to try and install into you curiosity into these topics so that you go away and try and learn them yourself, but give you the groundings into how you can go about that. Unfortunately, I am up against a few biases, and these are biases that you probably aren't even aware that you have, but they're probably there. And these biases come from community. Community is great. It gives us a sense of belonging. It gives us a place to bounce ideas off, and it is needed. And communities generally form around topics, so they'll splinter off from a larger community when they start to disagree with the direction that community is heading, and it starts off quite small, like a shanty town somewhere else. And what happens is people start to pass through this community. Some people stick around, other people don't, but even the people that pass through that community are going to leave an imprint. Because it's a small community, it's hard not to leave an imprint that you were there. What happens over time is that experts start to arise in this community, the leaders of that community. The thing that ends up happening is that the System 1 part of your brain, when you join this community, you read their blogs, you follow them on Twitter, you read their code. And System 1, because System 2 is lazy, System 2 says, you trust this person. Let's extend that trust just a little bit. So they're an expert on this topic, and you've only ever seen them being an expert on this topic, but because of that, we'll trust them in other such areas. A good example of this is infomercials. You'll always see those dodgy medical infomercials. They'll always say, doctor approved. That's because we as a society tend to trust doctors. So they're exploiting these biases in you. And what ends up happening is that as that community gets bigger, the walls around that community start to also get bigger. And what ends up happening, because you implicitly trust these leaders, they end up becoming the gatekeepers to our communities. They're the ones that give or take what ideas are allowed to enter into our community. So the other bias that I'm up against is one that is of personal effect. Personal experience has a higher weighting inside your brain than most other things, and the brain will actively sub out questions for a much easier one based on personal experience. So if I was to ask the audience, do they think the intelligence of the world is getting less over time? You're going to be biased by this. For any Americans in the crowd, our Prime Minister is female, atheist, and depending on what political party you listen to, is a liar. Now, the other thing that our brain is good at is storing negative experiences. There's a few papers around. The ones that I could find sort of said that it's basically 2 to 1. For every 1 positive experiences, for 2 negative experiences you have, has more weight than any positive experience. So it takes, if you've got 1 positive experience, if you've got 2 positive experiences, 1 negative experience can override that. So when I ask you this question, even though that you cannot answer that question, unless you've been reading papers, there's just no way that you can know that. You do not have the sample size, you do not have the statistics. You're going to think back, you're going to think to the last time you probably had an interaction with someone that made you angry. Due to the fundamental attribution error, you're going to attribute that to stupidity. And you're going to say, yes, humanity is getting less intelligent over time. However, the evidence is weighted in the other direction. There's actually every 10 years we seem to get 3 IQ points taller. And because of this, eventually communities start to tear down their walls. They start to tear down their bridges so that they can't have access to anything else. They've solved all the world's problems and they don't need any new ideas. This is a problem because it starts to ignore history. We think that we're better than everyone else. Take, for example, the recent spate of Ruby exploits. There was an exploit inside the Ruby JSON deserialization which allowed execution of remote code. This error plagued Java web frameworks in their early inception too. If Ruby developers had not ignored Java and sort of learnt from this, then, well, you can see the problems here. So one thing that I'm using the wrong slide deck. That's okay. So one thing that we as a web community sort of tend to try and ignore, we're getting better at it, is performance. We tend to think it's someone else's problem. So we use things like Heroku, we use MongoDB. So we're all for performance as long as it's not us that does it. So this is somewhat of a problem. And Moore's law is it's a law that seems to have held true over time that states that every 2 years the number of transistors doubles. And if we take a physical example, there is the iPhone, which was released in 2008. It shipped with a 412 megahertz processor, and in 2 to 3 years it doubled. It seems to stand true. But then there's also Wirth's law, Gates' law, May's laws, Page law, and they all say the same thing, that software gets slower at a rate that negates Moore's law. This was the first sort of invocation of this sort of appeared around the time Java was released, so maybe it was just talking about that. But it does sort of stand true to JS as well. Thanks to John Bristow for this. I had a much uglier graph, but Telerik apparently can make better, prettier graphs. So as JavaScript engines get faster, we as developers seem to abuse that. And as you can see, from 2011 to 2013, the amount of JavaScript that we've given doubled. So it seems to line up as well. And the orange line is the page speed rank. And it's sort of trending in the direction of Wirth's law. Is software getting more complex? Well, I went to the Computer History Museum recently, and they had a PD1 that they restored. There was a talk by a guy named Peter Sampson, who wrote one of the first music synthesizers on this thing. This is a machine that has 200 kilohertz, not megahertz, kilohertz, and 16K of RAM. And you can play Space War on this machine, which is for anyone who's up on their computer history, this is the game that sort of birthed Unix. So we were waiting in line to play this game, and someone pulled out their iPhone that had a copy of Space War on it. And does anyone want to take a guess at which one was more responsive? So it's exactly the same application running on like hardware orders of magnitude faster. And not only that, has a discrete graphic unit that's capable of pushing massive amounts of information to the screen. This thing, you had to tell it was each individual pixel on or off. And this thing topped it. Well, why is that? Well, for me, it's constraints drive creativity. Sorry, Agnes. They had constraints of the hardware. They had to sit down, they had to think about what every single instruction was doing, what every single clock cycle. They had to make sure that they were getting every single thing out of it. We have so many clock cycles per second, we don't care if we stall for, if we crash a pipeline and the process stalls for 2,500 cycles, we don't really care because it's running so quick these days. And for me, that's because we've invented phrases that build these somebody else's problems. This is a quote by Douglas Adams. So we as programmers have got phrases that build these things. We've got, we need to fail faster. It's a premature optimization. We need to ship. And eventually it becomes someone else's problem. So can we go back to the basics? Can we go back to computer science 101? And can we get performance into that system 1 part of our brain? So if I was to ask you what's 1 plus 1, you'd see that you'd know the answer. It's just there. You don't even have to think about it. It's just sort of magically floating inside your brain. And you might argue that that's a fairly easy thing to do. 1 plus 1 is not hard. But if I was to put this on the screen, any web developer in this audience could instantly tell me what that does. And again, it's that same thing. It's system 1. You don't have to think about it anymore. Fortunately for us, there's a system inside computer science called Big O notation. that allows us to rationalize about performance without having to worry about software, without having to worry about the hardware it's running on. And it means that we can talk about algorithms, functions on a level playing field. So we've got linear time, which basically just means that we have to look at every item inside an array. Or, it just means that as the input increases, so does the time the algorithm takes to run or our function takes to run. The next is we have O1, which is constant time. It means no matter how large our input set gets, the time it takes to look up an item takes the same amount of time. An example of this is like object properties on an object. Every time you look that up, it goes directly to that property. It doesn't have to scan through a list. And you can do this through using data structures like a hash table, where a hash table turns, say, a string into an integer. It puts that integer into as an index into an array and pulls off the data. And it looks something like that. It just jumps straight to it. Then we get ON squared, which is like linear, but it just means that it's squared based on the amount of input. So you can think of that as trying to find a sub-element inside an array, trying to find duplicates or things like that. And then we've got O log n. This basically means that we can halve the guess space on each time. An example of this is a binary tree. So we start with a root node 10, and then when we insert some data, we ask the question, is it greater or less than based on the comparator? In this case, 4 is less than, so it goes to the left. Then we insert 15, and it goes to the right. Then if we continue that process, we get what's called a binary tree. The good thing about this is, now if we want to search for 5, we start at 10, and then we move to the left. As you can see, we've now halved our guess space. We've completely wiped out that entire left-hand side of the tree. You can see where this gets beneficial if n is very large, because it means that as n grows, the amount of work gets much less. Then we've got animations are still there. That's a shame. That didn't work. So that's a tree. Basically what happens is you take the word you want to insert and you split it based on the start character. And then you build, and then when you want to insert the next one, say it's 2, well, we look for the node that started with T, and then we put the O next to it. What this means is when we're looking up data, the complexity is now OK. It means, well, OK, based on the key length rather than the input length. So this means that things like a drop-down, autocomplete drop-down can become much quicker. You do take the cost in space, but it becomes much quicker to look up items. Because we can just walk the tree in the same way that we do a binary tree, and we can find things much easier. So these are the... Now I have to run through the animation again, sorry. Apparently when you copy and paste, it takes the animations with it. And then there's n log n, which basically just means that every time we split it, we have to search through the entire split rather than just being able to keep splitting. So hopefully you can see how this sort of abstracts us away from programming languages, away from hardware, and gives us a way to talk about our functions and compare functions together so that we can talk about performance without having to write a line of code. We can take, if you're a Stack Overflow programmer and Google something, you can then look at 2 functions and go, that one's going to run faster for me, and take that one. Or you can look at your code and say, well, we've profiled our code, I'm looking at something, I can't sort of tell. Well, now you've got a way of looking at functions and going, this is the one we need to optimize because that's the one that's got the higher complexity. Yes. Another thing that we as a web community sort of rally against for some reason is functional programming, which is quite weird given the history of JavaScript. So I'm just going to give you a brief primer on functional programming and some of the things that it enables us as JavaScript programmers to do. The first thing is that functional programming is functional. It's not functional. So it's not functions that we're used to in JavaScript. It's based on a system called lambda calculus. Lambda, yeah. Sorry. It uses the lambda symbol to build these things, and they look something like this. This is called a lambda abstraction. You use the lambda symbol to indicate it's a lambda calculus. Then you introduce a variable named x. Then you've got the dot, which sort of separates the argument from the function body. Then we've got a function body, which is just x, and that's what gets evaluated. That's all well and good, but it comes with a bunch of different types of reduction. This is a beta reduction. So we simply just say, for every instance of x, we're going to replace it with 5. And we evaluate it, we get 5 back. Now, one of those cries that people sort of claim is that maths is not programming. I'm going to borrow a thing from maths to prove that wrong, and that is proof by contradiction. Proof by contradiction states for any theorem that you can prove wrong by using values that prove proof wrong is not valid. So, lambda calculuses have found their way into programming languages of all types. The top one's Ruby's lambda syntax, and the bottom one's C#, CoffeeScript, and JavaScript's fat arrows. So there you go, maths is programming. So that's a fairly trivial example. What else can we do with these things? Well, now we've got a much more complex lambda calculus. We've got x, and which our function body is then another lambda calculus which introduces a variable y, and then we add the two together in that function body. So if we were to do the same reduction, we get y to 5, and that's a result. We've subbed in 5, and then it returns us back a function. Well, the astute of you among there notice that this is first-class functions. But there's also something else present in there. Y is what's called a free variable. And for those of you that can give the Wikipedia definition of closures would know what that means. It means that we've now defined closures in a mathematical context. So, you know, x plus blah. That's how we do it in JavaScript. This was defined in 1930. There's 3 things we've taken from 2 examples of a paper written in 1930 that show that math concepts find their way into programming languages all the time. It wasn't until 1975, as far as I could tell, there was papers written on how we could apply this, but I think it was 1975, in the era of Fortran and COBOL, that we see this introduced. And this is Scheme. For those that know your JavaScript history, this was a language that heavily defined the direction of JavaScript when Brendan and I first wrote it. So I mentioned that this isn't functions as we know it, and that's because most of our functions that we write introduce side effects. As you saw when we were evaluating this, it only could deal with the input and the output, so it could only turn x into 5. This is a phrase called referential. This is what gives us what's called referential transparency. It was a term phrased by a guy named Quine in 1960, again, in the era of COBOL and Fortran, well before JavaScript or Scheme. And it basically means that we can change a reference inside a context and it retains the same meaning. So a context in the terms of philosophy is, I drank some delicious, and then I've put angle brackets to indicate a whole, or a context, as Quine called it. So if we substitute a phrase in there, I drank some delicious alcohol from Scotland, and then we change that reference to Scotch, because Scotch is the only alcohol that Scotland ever produces that's worth drinking, that keeps the same reference. So the reference has changed, but the context has remained the same. How does this relate to programming? Well, if we take the function that we defined in the first thing, what's called the identity function, we give it x, and it returns x. Fairly simple function. So if we apply that function, 10 plus id of 5, that's going to give 15. What referential transparency gives us is the ability to take that function out and substitute in that value. So to highlight what I mean by this, if we were to rewrite the identity function to be a little bit more complex, it updates a global variable. It now writes that global variable plus the input into the database and then returns x. We couldn't do that, because if we replaced it with the value, then the database doesn't get updated and our global variable doesn't change. And this gives us something that's probably important to every programmer: sanity. How does it do that? Well, when you're reading code, and we spend more time reading code than we do writing code, it means that you don't have to keep global state in your head anymore. You just have to keep values in your head. What value does this function return? It helps when we're writing tests. If we wanted to write a test for that identity function, and then someone else comes along and writes another test, and they say assert y is 30, What happens when our test suite gets so large that we can't run it in any meaningful amount of time to get results back to the programmers? Well, we do what any sane person does, and we start to split those tests out into different servers inside our test farm. What happens if the test that calls identity and the test that checks the value of y is 30 gets put onto different servers? That test is going to fail. And this is why referential transparency is so important. It gives you, as a programmer, sanity, the ability to reason. It becomes much easier to debug, and your code is much easier to write because it makes you hide side effects away into one area of the system. So another concept from functional programming is higher order programming. And this sort of just basically means using functions as data. In JavaScript, we've got the concepts already. We've got map. And for those not familiar with map, it takes an array. You then apply the map function and give it the function. In this case, we're giving it math.ams, but you can put any function in there that does something. And this takes a negative array and turns it positive. So what this is doing is, instead of us worrying about how we iterate an array or where our data is coming from, we're simply concerned with what we want to do. So in this case, we just want to turn things positive. So we can write it for the simple case of just turning one item into a positive and let something else take care of the iteration for us. Then we've got filter. Filter is a similar case. It takes a predicate, which is a function that just returns a Boolean. And simple thing here, we want to get anything that's positive. So we just return that Boolean of, is that item positive? And it simply returns as 10. That's broken now. Then we've got reduce. So we can take, this one's a little bit more complex, but it's probably one of the most useful one of these functions I find. It basically takes an array and turns it into a single value of that type of array. So in this case, we're reducing 10 to 60. So it does that by using a seed, which is an initial value, and that gets passed in on the right there, the 0. And then we take that seed and we add it together. So to visually represent what's happening here, the first function invocation happens, and we get 0 and 1, that initial value, and 1 coming in from the array. So we evaluate that, then the result from the top function gets passed in, and we continue and continue until we get to a result. So if we take these two ideas, referential transparency, and we take map and we take reduce, it gave birth to map reduce, the paper written in 2004 by Jeffrey Dean, who is quite famous inside Google, because apparently there's like a page full of like, what's his name, jokes, like things like, Jeffrey Dean doesn't need to compile his code, he just does it to find bugs inside compilers. Or Jeff Dean puts his pants on one leg at a time, but if he had more legs, you would see that his approach is O log n. And so what it enables to do is batch large amounts of data and query on it in ridiculously fast amounts of time, because we could take one of those map functions and farm it out to 1,000 servers. We could split up an array into 1,000 segments, send it out to an array, send it out to a server, and it ran that map, and then we do the same thing with reduce. We couldn't do this if those functions weren't referentially transparent, or if they resulted in mutated data. If you think about this, if it was updating global state, it was updating global state on A, and it was updating global state on B. A needed to wait for the global state for B to update so it could run its function. B needs to wait for A. Suddenly, no more data can be processed because we've reached a deadlock. So this is what referential transparency gives. It reduces the complexity of the code we have to write because we're only dealing with values. We're not dealing with values and time. So you might be, we're JavaScript programmers, we've been doing this for a long time. Node.js is built on the premise of higher order programming. But if we were to ask a Java programmer what they thought of higher order programming before the invention of Google Juice, or even with it, they'd probably say, it's not something you should be doing. And that's because to do it, you have to implement an interface that is called func. It takes two types, A and B. It returns a B and takes an A. Then to use it, you have to write code that looks like this. Now you can understand why a Java developer would probably not be so receptive to the idea of higher order programming. Because they have to write code like that. It's not native to the language. So syntax does matter. But syntax can matter to the point where it muddies the intent of what we're trying to do. So if you were trying to teach someone higher order programming, you wouldn't teach them in Java. You'd probably teach them in JavaScript. You'd teach them in Scheme. So when you're first trying to learn a concept, it's good to abstract the concept from the syntax. So don't let the syntax, don't let those biases of this is ugly overtake your ability to learn a new concept. Having said that, we're going to look at something called higher, well, I made it up, but so here's some JavaScript that we probably write nearly every day. We take some data, it's nested in multiple levels, and then we want to do something with that data. The problem is here that if speaker 1 was null, this would result in an error. So of course you don't. There we go. So if it's null, now we have to write code like this. And it becomes harder to see what we're actually doing. We're starting to hide behind multiple layers of syntax what we're actually trying to achieve. But we're good JavaScript programmers. We know how to get around this nesting problem. We do it all the time with asynchronous programs. What's something we can do? Well, we can do the usual thing. And start to put things into their own functions. And then we can write code that's at least naming what we're doing, where it's much easier to follow. But the problem is that we've now got repeated code. We've got code that's checking if an object exists spread out throughout these functions. So another thing we can then do from there so we can take that idea of checking for the existence of an object, and we can put it into a value, and then we just create a bunch of functions that do the checking for us. Then we can compose them together to build an object that, if it's there, then we output. And it's probably a little bit easier to read. There's no replication. But the problem is that we've got this getValue function sort of just floating around the global scope. We could potentially attach it to the object, but then we're attaching behavior to data. And this is a problem if we ever need to update the data, or the behavior has to go with it. It also becomes a problem because then we can't share it. It's linked to that particular set of data, so we can't share it around. We're JavaScript programmers. We like micro libraries, so is there something we can write that helps us abstract away this? And abstraction is the idea of, abstracting out what changes. And in this case, what's changing? Well, it's the idea of existence that's changing. It's the existence of object and object key. That's what's changing. So let's build us an object that abstracts away change of, it extracts away existence for us. So we've got the same set of data. We now have this function maybe. Maybe the object exists. It takes data, this.x, assigns it to an object. Then we just set up a helper function, this.empty. Now this is all well and good, but we have exactly the same problem. We're still putting this concept of null throughout our system. We've just called it isEmpty this time. While it does become more readable, it's still null. We still have to write that same check. So what we want to do is we want to be able to use that concept of higher order programming. We want to write a function that simply describes what we want to do with the data, not how we deal with that data. And we do this with this chain function. So chain takes an f, or a function, and this is that function that defines what we want to do. We check if it's empty. So this object's doing the checking. We no longer have to do it. It's taking care of that for us. If it's not empty, we simply return the result of that function applied to, and we pass in the value as an object, as the argument to that object. So here we are, we've taken that function, removed the null check, and now we're just returning a new one of those. The reason we want to do that is because we want to be able to compose those functions together. We want to be able to keep a chain going, sort of like we did with promises earlier. This is just a helper function that creates a new one of those. So what we do is we pass in maybe of conference, and then we simply just chain our functions together. And then at the end, we want to do something with that, so we map. We just use higher order programming again to say, when we're done with that, I want to do something with that data. So what we do is we're going to alert that data. So now we've removed the concept of null from our code. You'll notice that our calling code no longer has to worry about null. It just tells us what we want to do. We've pulled null away from the rest of our system. I don't know. I call that a win if you're me. One other thing that higher order programming gives us is monads. Now the thing is, if we maybe monad, you've just learnt monads. That's all it is. It's the idea of removing something from our system so that we're able to focus on what we want to do, not how we do it. So I don't want to have to worry about how null is handled in my system. I just want to say, I just want to output data. That's all I want to write. I don't want to have to write those nasty if checks. So it's the idea of putting these checks inside a box, basically. You can't look inside the box. You have to ask the variable to handle that for you. So we put null inside the box, we give it a value inside the box, and that box then handles everything for us. If you want to look into it, we take the lid off, we shove our function into that lid, and it gives us back a result. That's it. That's all there is to it. These two functions, chain is bind, or it's pronounced that, and of is return. That's all it is. A monad is two functions. There's something inside our industry that seems to have a lot of fear around them. They do have three laws: the left identity, the right identity, and associativity. These are all concepts that you learnt in maybe primary school, so don't be scared of them. I don't really have time to go into them too much detail, but it's worth learning. Again, it just describes how these functions have to behave, and it gives you some standards ways so that you know that when you call these things that they do compose together well. So recently there was a bit of internet drama, I think is the word I'm looking for. Standards plus academia. It's a phrase that we seem to use to dismiss ideas. That's academic. It's not worth learning. The thing with JavaScript is we have no type system. So in absence of type systems, we need standards. There's the promise standard, which we've seen today. Brian McKenna, a very smart individual for how old he is, I think he's 22 or something now, wrote the Fantasyland spec, which is a response to an issue raised on the promise spec. I think it's bug 94 if anyone wants to look at it. And he wrote a blog post that noticed that the promise spec is very close to being monadic, but not quite there. And things being monadic gives us things for free. I don't know about you, but I like free things. We all like free things. So if we write things in a monadic way, we get things for free. We get to just focus on the fun stuff. We get to focus on what we want to do. We don't have to worry about how. We get assurances that our code is going to run. We get assurances that null is never going to leak throughout our system. We get assurances that if we conform to this spec, we get a whole lot of library functions for free. We can get map for free. We can get lift for free. Lift is taking a function that you've written and pulled it up into that, basically pulling that into the box. So if we don't conform to that, we don't get that. And what does conforming to it get us? Well, if we go back to this example, it's not too hard to make the leap from maybe a value exists to maybe a value exists in the future. They're very, you can see they're sort of related. Like, so that's what the promise monad gives us. We've got maybe up here, the same one I just showed you. Now we've got the promise monad. So monads are not a singular thing. They're a concept of removing something from our system, or not removing it, but hiding it away from us. So you get the maybe monad, which hides away the concept of null. You get the promise monad, which hides away the pain of async programming. You get the I/O monad, which hides away the idea of I/O from us. You get the writer monad, which is really useful for writing logs. But you don't need to annotate classes, get loggers and things like that. It's much cleaner. Again, we just return a new promise. There's a few helper methods that get annotated to it to make it conform a little bit to the promise spec. Then we've still got the same function. We've got our chain function. We have our of. So they're the two functions you need to implement to be monadic. That's it. Unfortunately for us, there's no library that exists yet that will return a promise that is actually monadic, that is actually immutable, that conforms to these things. With the current promise spec, you can't pull a value out of a monad without breaking the monad. You can't do it without introducing side effects into your code. So all I'm doing here is just wrapping. I've got my same get value function. I wrap it and get the promise. Then using node, I just pull the file off using a key. Blah 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 blah. If we had a library that returned us promises in this fashion, you wouldn't have to write that code. You would just return. You just add the return there, and it would work. So again, it's the same code down here. I haven't changed my calling code, and I'm suddenly able to read things off the network with only updating one function. For me, that's quite a huge win. Like, how often can you do that? Now, this is the thing that if we conform to this monospec, that other people can write these things for you, and you can just substitute them into your code. Like, for example, I could have this code here, and I could have this function here in production, and then swap out my maybe code in tests, and I don't have to deal with mocks as much anymore. I can just simply swap out a function. This is what conforming to this monad spec gives us. It gives us the ability to focus on the fun things, writing the code we want to write. We don't have to worry about the edge cases. We don't have to think about every single possible case that it could fail because someone's done that for us. And this is why it's important for people to go out, to stop being anti-intellectualism, stop this current trend of anti-intellectualism. There wasn't real much debate. There was a lot of people just saying, this is academic, we can't do this because this is academic. We can't do this, this is a fantasy land. As I've shown you, it actually has practical applications in code that we write today. And for me, it's quite a worrying trend that we're introducing anti-intellectualism into this community, because high school for me was absolutely horrible. I was constantly made fun of for doing math problems that weren't part of homework. I was reading books that the English teacher didn't prescribe. And for me, the programming community embraced me. And for this programming community to start to reject the same people that were drawn to this community is quite a worrying trend for me. So please go and read the Fantasyland spec. It's filled with words like monoid. It's filled with words like applicative. It's filled with words like functor. If you understand map, you understand functor. Monoids are quite simple. They have a very scary word. The reason that it's written in such language is because math has clarity in its language. Monoid means monoid to anyone inside the mathematical community. English words mean many different things to many different people, so that's why specs are written in such a way. Monoids are easy. Addition is an example here. So take some time, learn it, and figure it out, and hopefully I've shown you why it's an important thing for us to follow. Another thing that we in the web community seem to reject because JavaScript doesn't have them is types. One thing that is often said is that types replace tests. You can't types can't do everything. You still need tests when you're dealing with a type system. Many people have been burnt by Java's type system, which is quite weak and gets in the way. Tests are slow, and with types you need less tests, just because you can test things. For this demonstration, JavaScript is untyped, sort of. It has one type, value. What do I mean by that? So if we were to quote the accepted definition of a type system is a tractable syntactic method for proving the absence of certain program behaviors by classifying phrases according to their kinds and the values they compute. Quite complex, but tractable just means it's easy to control. Syntactic method offered, obviously that's something that's typed, something that's static. So this is why JavaScript doesn't have types, because all the type checks are done at runtime. So when we build a program, it has one type value, and at runtime it gets filled in with a discrete union of string, function, something like that, and then makes behavior based on these things. And the interesting thing here is it proves the absence of certain program behavior. So it doesn't prove that your program is 100% correct. It proves that that program is 100% correct given the type that you've given it. But it proves the absence of things. So for example, if our program was 15 plus 5, we've proved, based on the result, that we haven't tried to add a string here. So we haven't tried to add 15 to Jared. We've proved that we haven't tried to add 15 to null. This is what a type system gives us. This proves that certain program behaviors have run. To read types, most people use Haskell's type system. If you ask a Scala question on Stack Overflow, someone is inevitably going to respond with, here's the Haskell type signature. They're quite easy to read. This is a function. It means that I take an A is a type, so it's anything, and I return the same type. If we want a function with 2 arguments, it looks like that. It's a method called currying. It's interesting. And basically what that means, if you give it a string, I get a string back. So it would be that in JavaScript. Then I take an A surrounded by these, and I give you back an A. That just means I take an array of strings and return a string. And again, this gives us something that's important, which is sanity. If you can't describe your function using one of those types, I highly recommend it's time to rewrite it, because it's going to be hard to reason about, and reasoning is important. It's going to be hard to understand when you're, again, having to read the code, because you have to think about what that function's doing. You can't just look at it. You have to understand the context in which this function's being called. And while we do sort of understand coercion, wouldn't it be better to not have to understand that? Wouldn't it be better to say, this is 1 plus 2, this is going to, I don't have to think, is B and N, so that's going to, it's much easier. But it gives us something else. It gives us something for free on most modern JavaScript engines. So if I define a simple function, add, I add A plus B, and I invoke it like this. Now if I was to invoke that, say, 100 times, and then hook up Java V8's deopt and crankshaft information, if we look at the last line, it says optimizing add. Second last line says marking add for recompilation, reason small function ICs with type info. Optimizing add took that, and that. So nearly 1/10 of a second to optimize. So what it means, ICs with type info, it means that in V8 terminology, what's happened is we've run the function, we've run it enough that V8 will mark it as hot, meaning that it's primed for optimization. It then consults its type oracle. Type oracle just sits there and watches the function invocations and says, you called it 100 times. You called it 100 times with what it calls SMIs, small integers. And you only ever return small integers. So I'm going to write you a new function that has the same semantics but returns you back that's optimized for dealing with exactly those types of options. So in x86, this means it's using the add instruction. So it's one instruction to add rather than having to parse off the value, turn it into an int, and blah, blah, blah. But the second we do this, the second we call add with a string, and 2, while this is correct in JavaScript, and it will happily return you 3. I can't remember coercion rules, it's tired. Or it could be 12, either way. It says, jump tail entry, deoptimize, bailout 2. So it now has to deoptimize that function. You've broken its trust. And so for free, if you think up front, this function is only ever going to call this, and write code that only ever calls it with those types, for free in every JavaScript engine, well, I think so. Who knows what Chakra does? They sort of keep their lids tight. But I assume that they're using some sort of JIT. You get this for free. You get performance. You're not fighting against the engine. The engine's going to be working with you and make things better for you. So the way that V8 does this is the assembler from that function. So for every single argument you pass into the function, it has to move it into a register and then does this test. All it does is doing an AND, and if it fails that, then it bails out and deoptimizes. So a guy named David Herman, a ridiculously smart man and also ridiculously patient. He sits on the ECMAScript thing for Mozilla. He realized that all these things were taking time. If you've got 16 arguments, it has to do this 16 times, and the checks for objects are much more complex. It has to consult its information to see if it's been mutated. So they came up with the idea of ASM.js. And for me, this is one of the most exciting pieces of technology that's come out this year. If you've seen the tech demos, Epic Games ported the Unreal Engine to browsers, and they did it in something like a week, like using Nscripten, which is an impressive amount of time to import the entire game engine. But the thing that's more impressive is the fact that it ran at basically native speeds inside the browser. I highly recommend you check out the demo. So what this does, what Mozilla has done is they've put an AOT compiler into the browser, which is an ahead-of-time compiler. So instead of a JIT, which is just in time, so it'll do a lazy compilation, and just in time for you to run it, it can go off and build that next function. It builds all that stuff up front. But because it introduces the idea of types, so we've got intish, boolish-ish. Because it has guarantees about the type up front, what it means it can do is it can remove all of these checks. It can generate those optimized functions straight up without having to watch your code, so there's no overheads, and basically builds they're getting speeds at like 1.8% native out of JavaScript running in a browser, which is absolutely phenomenal. So that's the end of my talk. I want to end it on be curious. There's a whole world out there that gives you stuff for free. There's a whole world of stuff. Like I showed you examples from mathematics from 1930. Imagine what would happen if we paid attention to the next 70 years of maths. What concepts can we pull out from there? I've shown you ideas that from other programming languages that we get performance boosts out of JavaScript engines to use. So we shouldn't close our walls off to other languages. We should embrace them. And most of all, have fun. Thank you.